Welcome to the video lecture on numerical integration. Up to this point, we've learned how to integrate a lot of functions, especially now that we have new techniques like pattern recognition and U substitution. However, there are still many elementary functions that do not have antiderivatives that are elementary functions. Functions like sine of x squared, cosine of x over x, and square root of 1 minus x squared are not the derivatives of any elementary functions. Since we do not know their antiderivative, we can't apply the fundamental theorem of calculus. And we know that the alternative would be to find a sum of an infinite number of upper or lower sums using rectangles, but that probably wouldn't be accomplished because we would need to have summation formulas for things like sine of I squared or square root of 1 minus I squared, and we don't have those kinds of formulas. If we are going to use a finite number of areas to get an approximation, then there are methods that are more accurate than just using typical rectangles. So we're going to learn two methods today that will approximate the area under a curve when our typical methods like using the fundamental theorem of calculus don't work. The first method that we're going to look at is called the trapezoidal rule. So what the trapezoidal rule does is it takes a curve that we wouldn't normally be able to integrate because it doesn't have an antiderivative, and we chop it up. But this time, instead of chopping it up into n rectangles, this time we're going to chop it up into n trapezoids. So what we do is we create a trapezoid by slicing this up into various subintervals, and then you take the left endpoint and the right endpoint and you just connect them with that straight line between them, and that's a linear function right there. And this then creates a trapezoid coming down just like this. So area of a trapezoid we know is 1/2 the height times base 1 plus base 2. So the height is going to be this horizontal distance here, which is going to correspond to the width of all of our trapezoids, which is what we normally call our delta x. And then our base 1 is going to be however high the function is at this left endpoint. And then base 2 will be however high the function is at our right endpoint. So that might be, if this is the interval x sub I minus 1 up to x sub I, then this would be f of x sub I minus 1 plus f of x sub I. So that's your left endpoint plus your right endpoint. And then you take all of these trapezoid areas and you add them all up to get your approximation. So if we take a look at this specific example right here and this trapezoid, so we have this piece over here on the left, this piece over here on the right, this endpoint and this endpoint are being connected with a straight line, so there's my trapezoid. So what would be the area of this particular trapezoid? Well, again, my formula is 1/2 the height times base 1 plus base 2, and in this example, if we assume that each of these units from here to here is 1, then this horizontal distance going across goes from 3 up to 7, so that's a distance of 4. So my height is going to be 4. Then we'll assume our scale here is also going by ones. So that means our left height, our base 1 over here, is going up to a height of 4. So that would be base 1. And our base 2 goes up to a height of 5. So 1/2 of 4 is 2, 4 plus 5 is 9, so the area of this particular trapezoid would be 18. So if we generalize again, let's suppose that instead of looking at this particular trapezoid, we look at the trapezoid that's on the subinterval x sub I minus 1 up to x sub I. And we're going to assume that the width of our trapezoid is that delta x. And just like we do with our rectangles, if we want to make sure that each of our trapezoids has an equal height, then we're just going to take our interval from a to b and find that distance, so that would be b minus a, and we're going to chop it into n equal sized trapezoids. If we look on this particular subinterval, then the area of that ith trapezoid is going to be 1/2 times the height, and the height is going to be this distance going across, which is exactly our delta x. So I'm going to write down for my height this delta x, and then my base 1 would be this left endpoint, which would be this endpoint right here, and I want to go however high the curve is at that left input. So I want to go however high my function f is using this x sub I minus 1. So that would be f of x sub I minus 1. And then for the right base, base 2, I'm going to go however high the function is using that endpoint, which is now the right endpoint. So I'm going to find f of x sub I. And these two heights, or excuse me, these two bases get added together. So we have 1/2 our height times base 1 plus base 2. And if you want, you can substitute in for this delta x that b minus a over n. So this is what the ith trapezoid would have for its area. This would be its formula. So what we're going to do then is to find the area of all n trapezoids, is we're going to sum these up from 1 up to n. And I'm going to use this formula for my areas. So 1/2 my heights times my base 1s plus my base 2s. So you find that for each individual trapezoid, and then you add all n of them together. Okay, so if we substitute in here, or actually not substitute in, but break it down a little bit, let me actually expand out my sum so you can see a little bit more clearly what this is going to turn into. First of all, this b minus a over n is getting multiplied by that 2. So I'm just going to pull that out front, and I'm going to combine the 2 times the n and make it a 2n. And if we plug in I equal to 1, then this is going to be f of x sub 1 minus 1 would be 0, and f of x sub 1 would be just f of x sub 1. So that's base 1 plus base 2 for trapezoid number 1. Then we're going to add to that base 1 plus base 2 for trapezoid number 2. So if I is 2, 2 minus 1 would be 1. And if I is 2 here, then this is going to be f of x sub 2. If I do it again for I equals to 3, this is going to be f of x sub 3 minus 1, which is 2, plus f of x sub 3, and so on. And I'm going to do that all the way until I is n. So this one will be f of x sub n minus 1, and this one will be f of x sub n. So all I did was I plugged in each I value in for both of these, and I get a pair for each trapezoid. So this is from trapezoid 1, trapezoid 2, trapezoid 3, all the way up to trapezoid n. And what I want you to notice in terms of the pattern is that the f of x sub 0 at the front and the f of x sub n at the back are the only ones that occur once, but the f of x sub 1s occur twice, the f of x sub 2 occurs twice, the f of x sub 3s are going to occur twice, and so on up until that f of x sub n minus 1, which occurs twice. So here's what the formula turns into. b minus a over 2n, that comes from this piece right here. You get a single f of x sub 0 and a single f of x sub n, and then you get a 2f of x sub 1, 2f of x sub 2, and so on up to 2f of x sub n minus 1. So the coefficients down here across the bottom become 1, 2, 2, dot, 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 2, and then back to 1 again. So those are going to be your coefficients that you're going to be using for this trapezoidal rule. So what this trapezoidal rule is, it's basically just a formula, and we're going to use it in just a moment to approximate the area under a curve. In other words, we're approximating this definite integral from a to b of f of x dx. Now to turn it into the actual area under the curve, or the exact answer of this definite integral, we would need to take the limit as n goes to infinity of this right-hand side. And that would turn it into that definite integral exactly. Okay, so this is basically a formula. You will want to have it memorized. And you're going to be given the function. You're going to be given the a and the b and the number of trapezoids n that you're supposed to use. And you just plug in a, b, n. You will need to identify what your partition is going to be. And then you're going to plug in each of those endpoints into your function using this particular formula. Okay? Now I want to make a note here of the difference between the trapezoidal rule versus the midpoint rule because they look very, very similar. On the trapezoidal rule, you're taking a curve and you're chopping it up into various trapezoids where you take the left endpoint and the right endpoint and you connect them with a straight line to create this trapezoid shape. And the formula for that, or the summation notation for that, is the sum from 1 to n of this b minus a over 2 times n, and then you get that f of x sub I plus f of x sub I minus 1 plus f of x sub I. Now if I take that 2 and I put it underneath this, then this is actually the definition of an average, because when you find an average of two things in math, you add them up and you divide by 2. So this quantity right here represents the average of our y values. So it's the average of the left y value and the right y value. Okay? Now if we think about what the midpoint rule does, if you have your curve like this and you have a left endpoint and a right endpoint, what the midpoint does is it doesn't take the y values and average them. It's going to actually take the x values and average them. So it looks at this x and it takes the average of the two, which is going to be right in the middle. And then you go up that high on your graph, and then you create a horizontal line going across that it creates a rectangle. So this has the shape of a trapezoid, but in the midpoint rule you're still using rectangles. It's just that the height of that rectangle is being determined by the midpoint of the x endpoints. Okay, so the summation notation for the midpoint rule would look like this. It would be your b minus a over n for your width, that's your delta x, times f of x sub I minus 1 plus f of x sub I minus 1 plus x sub I all over 2, and all of that gets plugged into your function f. So here, this is also an average, adding two things up and dividing by 2. But what we're doing here is we're averaging the the x values instead of the y values. So here we average the y's to get this linear function. And for the midpoint rule, you average the x's, and that new x becomes your input into your function. So you actually only use your function once here, as opposed to the trapezoidal rule where you use the function twice because you're going to use it for the left endpoint and for the right endpoint. So trapezoids average the y's, midpoints average the x's. Now in approximating integrals using upper and lower sums, we are approximating the function f of x by a constant function in each subinterval. So for example, when we make our normal rectangle approximations, we chop this up into pieces and we create little rectangles by going horizontally across using either the left endpoint or the right endpoint. So when you go horizontally across, that's a constant value. That's a constant height going across. So that's a constant function that we're approximating our curve by. When we do the trapezoidal rule, what we're doing is we're chopping it up into little pieces, and then instead of approximating the curve to be constant on this little subinterval, now we're approximating the function with a linear function. So we approximate it with this little diagonal line. So we're finding the best little line that fits between those two endpoints, as opposed to up here where we were finding the best constant, which approximates the curve. So here we're using constants, here we're using linear functions. In our second approximation method that we're going to talk about today, we're actually going to be using quadratic approximations. So instead of taking this curvy function and making it a constant or making it linear, we're going to try and find the best parabola that fits through our endpoints. So this is called Simpsons rule, and it sort of finds parabolas that go through our points as best as we can. So something like this, and then we piece together these little curvy sections, and that together will give us an approximation to our curve. This method is named after an English mathematician, Thomas Simpson, and again it's called Simpsons rule. And it's based on the fact that there is always a parabola that will pass through any 3 points that have different x-coordinates and that are not on a straight line. So for example, if you look at this picture here, we have 3 points on our curve, right here, right here, and right here. If I look at those 3 endpoints, I can find a parabola that will pass through them. And this might look something like that. Okay, so you try to find the best fitting parabola through those points, and then we're going to approximate this area by finding the area under that particular parabola from this endpoint on the left to this one on the right. And notice I'm actually skipping that endpoint in the middle. I need to use it to get the equation of this parabola, but I don't actually use it when I'm thinking about endpoints. Okay, and then you would go to the next 3 points, starting where this one left off, picking up here and then the next one, and trying to find the next parabola shape that would go through those points, and approximating the area under that parabola using known antiderivative rules. We know how to integrate a quadratic function, so we could integrate those and get a good approximation under that curve. Okay, so this is called Simpsons rule. We're not going to go through the derivation of the whole formula. I'm just going to give it to you. It looks very, very similar to the trapezoidal rule, but one thing you'll notice right away is that instead of b minus a over 2n, now it's b minus a over 3n. You still have this partition using x sub 0, x1, x2, x3, all the way up to x sub n. The f of x sub 0 and f of x sub n are still going to have a coefficient of 1 in front, just like the trapezoidal rule, but the inside coefficients are a little bit different. The pattern for these coefficients are 1, 4, 2, 4, and then it alternates 2, 4, 2, 4, etc. until it ends with a 4 for the second to last piece and then a 1 for the very last piece. So it's 1, 4, 2, 4, 2, 4, etc., and then back to 4, 1 on the end. Okay, so those coefficients alternate between 4s and 2s on the inside. So this is called Simpsons rule. If you were to take the limit of this as n goes to infinity, then that whole right side would approach the true area underneath. So this is just, again, an alternative to that trapezoidal rule, and usually the more curvy your function, the more imprecise that trapezoidal rule or those rectangles would be, because you want a more complicated function to approximate it. So Simpsons rule is using quadratic, so that's going to increase the accuracy of your approximation. So Simpsons rule tends to be more accurate than the trapezoidal rule. Okay, and again, the idea behind this, or the picture behind this, is if you have a function, you're going to chop this up, and for Simpsons rule you need to make sure that you're using an even number of for n. This does require that n is even. And what you do is you take 3 consecutive partition points and you find the best fitting parabola that goes between them. So this one might look something like this, and then you find the area underneath that using that equation of that parabola. And then you pick up where the last endpoint left off, and you use the next 3 consecutive subinterval points, and you find the best fitting parabola that goes through those. And then you find that area underneath. Okay, and then you would go to the next 3, find the parabola that goes through those, and so forth. Okay, now when we calculate these approximations using the trapezoidal rule or Simpsons rule, there is going to be some inaccuracy because they are just approximations. So we can come up with formulas. We're not going to derive these, but there are some error formulas that calculate how much error is created by using the trapezoidal rule or Simpsons rule. So this is the error for the trapezoidal rule. And it requires knowing the b, the a, the n, and then we find a bound or a maximum on the absolute value of the second derivative of our function f. And then this is the formula for the error for using Simpsons rule. And it requires a bound for the fourth derivative of our function with slightly different coefficients. So I'm not going to expect you to have these memorized, but you might be able, or you might need to be able to use them to answer some questions, and we'll do an example in just a moment. Okay, let's go about practicing using this trapezoidal rule and Simpsons rule for a specific function. So this would be what a typical problem would look like. We want to approximate the integral from 0 to pi over 2 of the square root of 1 plus cosine squared x dx. Now first of all, the reason why we have to use trapezoidal rule or Simpsons rule here is because the square root of 1 plus cosine squared x is not something we know how to integrate. So there would be no way of us getting an answer to this integral. So what we're going to do is we're going to chop this up into 4 different trapezoids, or n equals 4 for Simpsons rule, and figure out what those formulas tell us for the approximate area under the curve, either using trapezoids or using parabolas. So step number 1 is to find your partition points, and to do that we need to find that delta x, that width. And to get delta x, you're using your interval that you're looking at. So this is going to be b minus a over n. So for our problem, the b is the pi over 2, the a is the 0, and I want n to be 4. So I'm going to chop this into 4 pieces. So this is pi over 2 divided by 4, which is pi over 2 times 1/4, which is pi over 8. Now once you know what your width is going to be, you can write out what your partition is going to be. Your very first partition point is going to be the starting value down here, that lower limit, 0. And then we're going to go up 1 width, so that's going to be this pi over 8. And then we're going to add another width to that. So pi over 8 plus another pi over 8 would be 2 pi over 8, which is the same as pi over 4. Then I'm going to add another width to that. 2 pi over 8 plus another pi over 8 would be 3 pi over 8. And I'm going to add another width to that. 3 pi over 8 plus another pi over 8 is 4 pi over 8, which is pi over 2. And that's when I stop, because that's my upper bound. So this 0 is our x sub 0. Pi over 8 is x1. Pi over 4 is x2. 3 pi over 8 is x sub 3. And pi over 2 is x sub 4. That's what we're going to use here, 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 and here. So for trapezoidal rule, this becomes b minus a, so pi over 2 minus 0, over 2 times n, 2 times 4, times parentheses or bracket the function evaluated at x sub 0, which is 0, plus 2 times the function evaluated at x sub 1, which was pi over 8, plus 2 times the function at x sub 2, which was pi over 4, plus 2 times the function at x sub 3, which is 3 pi over 8, plus the very last one does not have a 2 in front, and that's just f of pi over 2. So that's our trapezoidal rule, and when I simplify this stuff out front, pi over 2 divided by 8 becomes pi over 16. F of 0, now how do you find these f values? F of 0, you're going to go back to this function right here, the function that's inside of your radical or your integral. So square root of 1 plus cosine squared x. So if I were to plug 0 into that for x, cosine of 0 is 1, 1 squared stays 1, 1 plus 1 is 2, so this is going to be the square root of 2. Then we would have to plug in pi over 8. Now that's not going to give us a nice value back, so you're going to need your calculator for that. It's about 1.3615 for f of pi over 8, and then we need to multiply that by that coefficient of 2 out front. And then we want 2 times f of pi over 4. If you plug in pi over 4, again using your calculator, it's about 1.2247. And then for f of 3 pi over 8, when you plug that in, we want to multiply that by our coefficient of 2, and that's approximately 1.0707. And then when I plug in pi over 2, cosine of pi over 2 is 0, so this is 1 plus 0, which is 1, square root of 1 stays a 1. So here are my 5 different values: f of 0, f of pi over 8, f of pi over 4, f of 3 pi over 8, and f of pi over 2, and the 3 middle ones have those coefficients of 2. So you would multiply all of that by that pi over 16 out front, and again this is all stuff you want to do on your calculator, and you're going to approximately get 1.8686. Okay? Try to keep the values as exact as possible. Try not to round off. Now I rounded off when I was writing just to show you approximately what those values were, but I would recommend leaving these values and typing them in directly into your calculator. It's tedious, but it's going to give you a more exact answer in the end. Okay? So what changes with this problem if instead of doing it with the trapezoidal rule, I do it with Simpsons rule? So this is our approximate area using the trapezoidal rule. So what's going to change is a slightly different formula, but the delta x does not change. That's still going to be pi over 8. And the partition points did not change either, because we're still using 4 for our n. So our partition points are still going to be 0, pi over 8, pi over 4, 3 pi over 8, and pi over 2. So for Simpsons rule, this is just going to become pi over 2 minus 0, that's my b minus a, over 3 times 4, and we're going to multiply this times f of x sub 0, which is the 0 right here, plus 4 times f of pi over 8, plus 2 times f of pi over 4, back to 4 times f of 3 pi over 8, and then just 1 times f of pi over 2. So your coefficients should go 1, 4, 2, 4, 1. So other than the 3 that's in the bottom and the different coefficients in the middle, everything else is the same for how we did it with trapezoidal rule compared to Simpsons rule. So this is going to be pi over 2 divided by 12, which is pi over 24. And then you're still going to have those same f values that we used up here. We're just multiplying them by different coefficients. So f of 0 will still be root 2. Then we would want 4 times 1.3615 approximately, plus 2 times 1.2247, plus 4 times 1.0707, plus 1. And then you punch all that into your calculator and you get 1.9857 for this Simpsons rule. So this is the approximate area using Simpsons rule. Now, in general, Simpsons rule is always going to be more accurate than the trapezoidal rule. Typically, if you have a curvy function, you're going to want to use, a curvy function to approximate it. So instead of using lines, which is what the trapezoidal rule does, we'd probably want to use something that has a little bit of curve to it, like a parabola. So that's why our Simpsons rule is going to be a more accurate answer, a better approximation than trapezoidal rule would be. Now, in the next example, we're going to use that error formula. So we want to find the number of partition points so that the error using the trapezoidal rule to approximate the integral from 0 to 1 of sine of x squared dx is less than 0.00001. So think about how the trapezoidal rule works. Normally I tell you how many trapezoids n to use, and then you use your formula and you compute what that error area approximation would be. Well, this time what I'm saying is I know that I want my actual approximation to be really close to the true area, and I want it to be less than, that error to be less than 0.00001. So how many trapezoids, what n value do I need to use to make sure that my answer is that accurate? Okay, so the formula that we're using is this error formula right here. Okay, we want this error to be less than 0.0001. So that means we want this formula b minus a cubed over 12n squared times the maximum of the absolute value of the second derivative of x. We want all of that to be less than 0.00001. So do we know b, do we know a, do we know n? Yes. Or we don't know the n, but we know the a and the b from our integral. A is 0, b is 1. So I know my b and my a. That's just going to be 1 minus 0. We don't know the n. That's what they're asking us to find. So I'm going to leave this as an n squared. What I need to know in order to be able to solve anything here is this maximum bound on that second derivative. And that's not normally something that's easy to find. So what I am showing you here in this picture is some computer algebra system called Derive that will give us a way of figuring out what that maximum second derivative would be with its absolute value. So here's what it shows. Here's sine of x squared. Line 2 here takes the second derivative of that function sine of x squared, and line 3 is what that second derivative would look like. In line 4, I have the absolute value of that second derivative, and that's what this graph is right here. This is the absolute value of the second derivative. And looking at that graph, where is its maximum? This point down here is a relative min. So the only way you could have a max would possibly be at one of the endpoints. So what is this second derivative when x is 0? Because remember, our interval is from 0 to 1. So our two endpoints would be 0 or 1. So what is this when x is 0? It's 2. So that's this point right here. This is just about at 2. I kind of colored over it a little bit, but there is a little bit of distance between here. So this is a little bit lower than that 2.025. And what would be the height of this when x is 1, which is, just about over here a little bit? That would be up here. So I plugged in 1 into that absolute value of the second derivative, and that's this number right here. So 2.28527. So which of those is bigger? Obviously the 2.28527. So on the interval 0 to 1, this absolute value of the second derivative function takes on its maximum at 1, which is this value right here. So we can use that number, that 2.28527, as this maximum. So the largest value that the second derivative will take on is this decimal. So we plug it in, and this now just gives us an equation or inequality that we can solve for n. So 1 minus 0 cubed is just going to be 1. So this is 1 over 12n squared. And to solve this for n, what I'm going to do is I'm going to multiply through both sides by 12n squared, the thing that's in the denominator. So these will cancel out, and I'll just get 2.28527 is less than 0.00001 times 12n squared. And I'm going to go ahead and divide by the 0.0001 and the 12 on both sides so that I can try and get that n by itself. So we have 2.28527 divided by 0.00001 times 12, and all of that is less than n squared. And to solve for n, we would need to take the square root of both sides. And when you do that on your calculator, this whole value right here is approximately 137.99. And we want our n to be greater than that. So I'm going to round up to the very next highest whole number. So we would want our n to be 138. So I need at least 138 partition points in order for my trapezoidal rule to be accurate enough to get me the real area to within 0.00001. Okay? If I use less than 138, then my error is going to be too big. If I use 138 or more, then I'll be within the desired accuracy. Okay? Let's try that same kind of a problem, but this time for Simpsons rule. So same integral, 0 to 1 of sine of x squared, same error, but we want to figure out how many partition points it's going to require to be within that level of accuracy using Simpsons rule. So the error for Simpsons rule is this formula right here. Slightly different formula. And we want this error to be less than 0.0001. So we need our b, which is 1, minus our a, which is 0, all raised to the fifth, over 180 n to the fourth. I don't know what my n is yet, so I'm going to leave that as an n, times the maximum of the fourth derivative in absolute value. We need all of that to be less than 0.0001. So this would be too hard for us or too tedious for us to do by hand. That's why I'm using an algebra system to figure it out. So that's what this picture is showing us. Here's our sine of x squared. That was our function that we started with. Then I'm going to take the fourth derivative of that. That's what this is in blue. And then I'm going to take the absolute value of that function. And over here, the fourth derivative is the graph in black. The absolute value of that is this graph in green. So the one that's all positive. Now to find out the maximum of this, notice there is a relative max. It looks like it's right here. So how would you locate that relative max? You don't want to just eyeball it because that wouldn't be very accurate. So to find a max, you look at critical points, which means I need to look at the derivative of this graph. So if this is the fourth derivative, then the derivative of the fourth derivative would be the fifth derivative. So that's what this is calculating right here. The fifth derivative of the sine of x squared is this equation right here. And then I can go ahead, there's a command on this algebra system that finds the zeros of that, which would be where those critical points are 0. And that's this x value right here. So at about 0.85, this is going to hit that little peak. And if I plug that in to the fourth derivative, we get negative 28.4285. If I take the absolute value of that, then this would be positive 28.4285. So we want the positive because this error formula assumes that you're using the absolute value. So the largest that this max takes on is 28.4285. So I'm going to substitute that number in right here. The numerator, 1 minus 0 to the fifth, is just a 1. So just like in the last example, to solve this, I'm going to go ahead and I'm going to multiply both sides by 180 times n to the fourth. So that'll just give me 28.4285 less than 0.00001 times 180 n to the fourth. And I'm going to divide both sides by that decimal and that 180. That's going to give me an n to the fourth. So to solve for n, what does it take to undo an n to the fourth, a fourth power? You need a fourth root. So I'm going to take the fourth root of both sides, and that'll give me my n. And when you plug this into your calculator, the fourth root of 28.4285 all divided by 0.00001 times 180, that is about 11.21. So you want to take at least one higher, right? So we want our n to be 12 or higher. So we need 12 or more partition points in order to get that desired accuracy. Now think about that for a moment. When we were doing this, we used the exact same integral and error as we did in the last problem. But when we did trapezoidal rule, we needed 138 partition points. That's a lot. Versus Simpsons rule, which only requires 12 partition points to get the desired accuracy. So that's proof that the Simpsons rule is going to give you a much more accurate answer faster than that trapezoidal rule will. Okay, so typically we prefer to use the Simpsons rule if we have a choice because it's going to give us a better approximation. All right, so for this lecture, what you want to know are your trapezoidal formula and your Simpsons rule formula. Have those memorized, be able to evaluate or approximate an area using those two rules for a given function, a given interval, and a given number of n. Okay, so we did a problem like that earlier. And then you won't be expected to memorize these error formulas, but you might be able to, you might be required to use them to find out how many partition points you need, for example, like in this example right here that we did. Okay? All right, that concludes our lecture on numerical integration. Good luck.